Actually, in 2008, I got a paper from Math Reviews, and it was by Mikhail Solodov. And he was, in that paper, he was talking about this simple bilevel problems. He didn't call it simple bilevel problem. He spoke about bilevel problem with convex objective or convex data. And there he figured out, he looked at a problem like this, which is very common, very natural. That when you are solving an optimization problem, a simple convex optimization problem, sometimes you want the nature of the solution has to be a particular type. Maybe it's a sparse solution you want, like you have seen in the talk of machine learning, or you might want a least Euclidean norm solution. So there are various requirements that you can pose on the solution. Once you do this, then you are essentially again trying to do some optimization problem where the feasible set of the solution set of the original problem becomes a feasible set of this new optimization problem. So here we are minimizing a convex function f over the solution set of another convex problem, another convex optimization problem. So I need to choose a solution of this convex optimization problem, minimizing h over c, so as to minimize another function f. It could be half of norm squared, or it could be just L1 norm, right? So this is called a simple bilevel programming problem. This term which we had used in a paper with Dempe and myself, Dempe and Dean way back in 2010. When I saw this paper first, in the paper of Mikhail, he gave an algorithm, which is we'll discuss at the very end of it. But I was wondering from that if this is really a bilevel problem, essentially we have taken out the second player, if you can think about it in this way. Then are the difficulties of the original bilevel programming still persists here, or something better comes out? Because the problem is finally a convex optimization problem, which is not true in the other bilevel programming problem, that even with convex data, linear data, doesn't matter. The problem is a non-convex problem. Here it is not. So does it have certain issues with, does the same difficulties go on? Or no, we don't have the same difficulties, but we have lesser difficulties, but some difficulties are still carried over. So let us see. So that was the question with which I started looking at this problem. And then, of course, at this moment, I have worked a lot on the writing algorithms for this problem, even algorithms which can beat what Solodov has done. So look at this sparse system. So in compressed sensing, this is a very important problem. So you find a sparse solution of the linear system. But now if you look at it, I can equivalently pose it like this. And this is exactly the SBP problem, the simple bilevel programming problem. So this is a very, of course, one can say that I can write it as a regularized problem, what Steve Wright was showing in the morning so the first talk. So that can be also done, but this is also another way of posing the same constant compressed sensing problem. Nobody has looked at it in the bilevel form, because now we have designed algorithms which can actually solve these problems pretty efficiently. See, the idea of having this problem and writing algorithms for this is that I actually do not solve this problem, the lower level problem, fully. But in one go, I select a solution of this problem which minimizes the function f. At one go, I do it. I don't have to solve it, this whole thing, and then try to figure out which is the minimum norm. In one go, I don't even bother I'm not even bothered whether I'm really trying to solve this problem. In one go, I am finding a minimum norm problem or a minimum L1 norm problem, L1 solution of this problem. So that's what is the power of this simple looking structure. And it comes up in many situations, even in engineering problems. For example, a problem which has interested me a lot is to find the error bound of convex to a optimization problem. Means you have a convex optimization problem and you have a solution set. And now given any point, maybe a feasible point, maybe infeasible, maybe a feasible point, right? X in C, I want to know an upper bound to this distance. If H is strongly convex, then this can be done because I can view it as a variation inequality, as a strongly monotone variation inequality, and then I can do things. I can use gap functions, I can write down error bounds. But if it is just convex and not strongly convex, then if it is, except if it is linear, then even there's a lot of literature on error bounds for convex inequality system. There is a standard assumption that Slater condition has to be satisfied in that inequality system. Argmin sets can also be written as inequality systems. But once you write the Argmin set as an inequality system, the Slater condition is immediately violated. And hence those error bound techniques that you know for inequality system cannot be applied here. So I have no clue, though I tried this a lot with John Borwein, and we could lift it to a higher dimension and then possibly get some idea. But otherwise, I have no clue how to do the upper bound for just when H is convex, not strongly convex or linear or anything. So then, but I can numerically estimate it. So you give me any point X, then I'll write down, this is the problem. To numerically estimate the distance, I really have to solve this problem, which is again a simple bilevel programming problem. In my last paper, which I'm just going to communicate in a day or two, that paper, we actually take real examples and show that we can actually estimate the distance very well by using our bilevel programming algorithms. So you can generalize this SBP problem very rapidly because you can, if H is a differentiable function, you can write it again as a problem with generalized equations. If you replace this grad H with some F, which is monotone, then this problem looks like this. And this is nothing but a variation in inequality. And then we come to this problem, which we call the simple MPEG problem. Now, this symbolism is very bad because in the literature, there's something called stochastic MPEG, and then they also use the same sign. But okay, within our fraternity, okay, let's call it SMPEG, simple MPEG. Now, there has been this problem has generated quite a bit of interest now because just I think this year in one of the issues of SIAM optimization, I just saw a paper. Okay, at the end of this talk, I can give the reference of that, which deals with algorithms for this in slightly different way than what I have also dealt with algorithms for this. So now, what kind of a problem can we have a problem like this? Now look at this very simple situation. So look at this primal there. I should write LD. So there's a primal pair of LP problems. This is a canonical writing of an LP problem. This is a dual. So now, suppose I want to tell you that find a 2-norm solution with minimum 2-norm primal dual solution, and that's pretty often asked. That I want a solution of the primal dual solution of the LP, but I want the minimum norm. Then, or even sparse, whatever. So then, an interesting way to do it is the following. This can be remodeled as a simple MPEG problem, because consider a VI like this, where the F function, the F of the VI can be written like this. This is an asymmetric matrix. So it's an asymmetric operator. So it's a skew symmetric matrix. So this is an asymmetric operator, and any monotone operator can be expressed as a sum of a subdifferential of a lower semi-continuous function and an asymmetric operator. There's in chapter 9 of the book by Jonathan called Convex Functions. So this structure, with this structure, I can construct a VI with the set C of this form. Then one can show that this is a monotone operator, of course. One can show that if this is the symbol of the primal dual set, then this is exactly equal to the solution of the VI. So this is a very interesting result. So then this question of finding this primal dual solution, the least norm solution, can be posed as a simple MPEG problem. Now, whether solving this is an easier thing or solving that is an easier thing is a question, of course. So, but structurally, these problems naturally arise. So what are the drawbacks of SBP? So suppose I know that the lower level has a solution. That has to have a solution, otherwise the problem is meaningless if it doesn't have a solution. So then let us call that lower level solution alpha. And if that lower level solution is called alpha, my single level reformulation would look like this. So this is called the reformulated version of SBP. And here the Slater condition is violated. Because obviously they cannot have HX set strictly less than alpha, then alpha cannot be the minimum. So Slater condition is violated. So this is a very, very important thing, because here what happens, the Slater condition, here what happens, the Slater condition is violated means what? The MFCQ is violated, because for a convex problem, Slater and MFCQ are the same thing. As a result of which, this is the difficulty which was there in the case of the other problem, the main bilevel programming problem, the same difficulty comes in. So just to give a taste as how can I write down optimality conditions for this? This is a very strange kind of situation, right? So here I have a thing from my book, so you have a very strange looking set, which is cone of this 0, 1 union cone of 0 alpha. I cannot now remember exactly all the details that I did. So you have to assume that this is a closed set. And then for any solution of SBP and hence of RSBP, they are the same. Then any X bar is a solution if and only if there is a lambda greater than 0 such that this holds. Writing this is very simple, but actually trying to prove this optimality when this kind of constant qualification is a very difficult thing. So optimality condition has always remained a kind of very strange zone in bilevel programming. Okay, if optimality condition holds, it's fine. If it doesn't hold, it's not fine. In fact, only very recently I found a paper, which I will mention at the end, where they have actually been able to handle write down algorithms for a very particular situation of the actual bilevel programming that I spoke in the main talk. But the interesting feature that lies here is that usually for bilevel programming, people had started using heuristics. The actual bilevel programming, nobody knew to write a nice thing. But for example, evolutionary methods by Professor Kalyan Mohadev, who was once my colleague here at Kanpur and is now shifted to Michigan. So he and his group had done a very good work on actually using heuristic techniques to get some idea about local solutions for bilevel. So here this is, but I don't find it anything more interesting because it's so difficult to handle such things. Here is an example where a simple example where you show that actually on this optimality, this constant qualification condition actually holds, and a very simple situation where, and then the optimality condition holds. Now the interesting question that comes, here is the interesting question. We knew that, okay, if I write if I write the KKT reformulation of the actual bilevel problem, then the bilevel problem and the KKT reformulation are not the same thing. That what we had discussed. But here, what is the issue? Let us see. That is the same difficulty transferred here. Okay. So if I write down the set C as GIX less than equal to 0, then the corresponding MPCG to the SBP is of this form. Right? We really have to solve this to get there. So are these are SBP and its MPCC version the same? Let us see. The interesting fact is that the huge difficulty that we had in the actual bilevel programming to a large extent vanishes here. Let us see what happens. Suppose we now have a blanket assumption that the lower level has Slater condition. So if my lower level has a Slater condition, then let us see what are the results here. Then if X bar solves MPCC, then for any lambda bar which is in the set of Lagrange multipliers, which is this set, Lagrange multipliers at X bar, then X bar lambda bar actually solves SMPCC globally. X bar lambda bar, if it is a solution of the SMPCC, this problem, Slater condition is holding at the lower level. Then, even if it is a local solution of SMPCC, then X bar is a global solution of SBP. Actually, this theorem, this result is proved by noting the fact that if Slater condition holds, then the Lagrange set of Lagrangian multipliers do not change. They remain fixed. Whatever is the solution, it doesn't matter. The set of Lagrangian multipliers remains a fixed set for every solution in a convex programming problem. So here is a very interesting thing, that this is a non-convex problem because it's a complementarity problem. But here, any local solution of this problem is actually a global solution. If you link these two problems, that is what will come. Here is an interesting example of a non-convex problem where local solutions can become global. Okay. So, but if the Slater fails at the lower level, then again, these two problems have issues. Now, the interesting fact is that this is the point where I have not worked yet, but I would like to now work. That here what happens is that if the Slater holds at the lower level, then you can always write down this problem, the SBP, as this, and then apply the standard results that you know for MPCC and the standard techniques and solve it. So this is an area that one has to explore, and that is yet unexplored. So what can we gain some better results than what we have with other algorithms? So here is an example where the Slater condition would fail at a lower level. The Slater would fail. So the G's are this, where C is given by these G's. And there's a linear problem. So Slater condition fails here because 0, 0 is the only lower level feasible point. So it's a very pathological situation. And then the MPCC, lower level MPCC is not even feasible. So that's the case. So in general, that the difficulty, these huge difficulties that we had in the actual bilevel programming is actually removed once the Slater condition hold, that is removed for this kind of problems. So we can now use techniques from MPCC to solve this, because once Slater condition is failing, to write down good algorithms with good convergence properties are pretty difficult for those problems, because they're doing the convergence proof is also involved. That is what I worked, and that is what we have found out. Now we are just I'm going to talk about another area which I like very much, is the gap functions for variation inequalities. And I will show how the dual gap function can be used to study the simple MPEG problem, convert the simple MPEG problem into a SBP problem, and then that would allow us to write a schematic algorithm for the SMPEG problem, simple MPEG problem, which has a convergence guarantee. So that's what we will discuss, this part. So given a variation inequality problem, a gap function is a function which would always be non-negative over the set C, the feasible set of the VI. And if GDX is 0, so or the gap function is 0 at any point, then that point is a solution of the VI. And if the VI has a solution, then GDX must be 0. So this is actually this is a if and only if here. So this is the nature of a gap function. So this is a very interesting gap function. This has been used in many convergence analysis in optimization, and this actually comes up from the Minty's variation inequality. This is when f is monotone. This is a gap function for capital this VIFC, and if f is not monotone, even it is still a gap function for the Minty VI. But if it is a monotone one, then it is also a gap function for the standard Stampacchia VI. And then this GDX is a gap function, and the GDX is convex function. But the problem is, even if you get the gap function to be convex, that allows us to use it as a very good explanatory tool, but it is very difficult to compute it. I've been able to successfully write down error bounds with Didier Ossel and Andrew Zhu for these gap functions for VIFCs using this gap function. But if you look at it, unless you have very special structures on F, capital F, like maybe they are affine or something like that, you cannot have you cannot compute the supremum so easily. Because here you're asking for every X, you get me a global optima of a non-convex problem. So computation of GDX is very difficult. But GDX can be computed in an approximate way, of course, but that's the difficult task. But otherwise, GDX by itself becomes a very good theoretical explanatory tool. Like many tools in non-smooth analysis or many tools in optimization, many tools are explanatory. They are not really one which you go and use in computation. For example, if you look at the notion of co-derivative, it's largely an explanatory tool, or even the subdifferentials in many cases. Hardly you compute them rather than the convex subdifferential. So let us consider in this particular case C to be a compact and convex set. Then I know that the variation inequality has a solution. The solution set is non-empty. And then what happens is that the solution set of the VI actually coincides with the argmin set of minimizing the gap function over the given feasible set of the VI. So which allows us to change the SMPEG or write the SMPEG equivalently as a bilevel programming problem, a simple bilevel programming problem. And hence, you can write the reformulated version of this bilevel programming problem. Now, the lower level objective function has become the dual gap function, and you have this sort of setup because here the minimum value is 0. So the value function is, so this value function reformulation is of this form. So it's a nice reformulation, very simple. Now, if you want to write an optimality condition for SMPEG using GD, then you must understand that standard BCQ or Slater condition cannot be used, because Slater condition would imply here that this is true. But Slater condition actually fails for this problem because there cannot be X in C for which GDX is strictly greater than 0. That goes against the definition of gap function. So here we have to use a weaker condition called the weak BCQ, where instead of this intersection is with the minus of the normal cone being empty, which is later, I say the intersection with the boundary of the normal cone is phi. So weaken it. If that weak BCQ or WBCQ holds, then you get an optimality condition quite simply of this form. Right. And of course, at the solution, you might ask me, where is the complementary slackness condition with GDX? So complementary slackness condition is not required because GDX bar is always 0 at the solution. And hence that is automatically satisfied. You want us to understand by using Danskin's results formula, it's because C is compact now. I can actually write GDX in this way. This is the convex hull of this, where YX is the active index set, the set of all Y in C such that this holds. Because obviously, because C is compact for every X, there will be some Y for which this will hold. Because this, I'm assuming F to be a continuous function, a monotone function, right? So the continuity of F is given. We are not getting into that details. F is obviously we are taking it to be a continuous function always. Okay. Now, what happened to this weak BCQ? Does it really hold? So here is an example where we show that weak BCQ actually holds. That the intersection of GD, the subdifferential of GD and the negative of the boundary of the normal cone actually is empty. So this is not a very difficult example, quite a simple example to go through. What is more interesting is a schematic algorithm. After that, of course, we have developed much detailed algorithm, but schematic algorithm is just a starter because, as I told you, that the dual gap function is a very good explanatory tool. It allows you to see certain things in a very simple way. So we choose an starting solution and an optimality threshold. And we are minimizing a function like this, where epsilon k's are actually going towards 0. One may say, okay, is it not a penalty function? Why you are putting epsilon k going to 0, not going to infinity? The idea is that as I increase my k, I gradually, because finally I have to have, see, if I make epsilon larger, I am putting more weight on minimizing GD. I am not putting any weight on minimizing this. So basically what would happen as I keep on increasing the sequence, as k increases, as I solve more and more problem, the weightage should gradually shift to the minimization of f. And as a result of which epsilon k should be tending towards 0. And what we could prove here is that taking a stopping criteria like this, because whenever g of xk is 0, we can gd of xk is 0, we can prove that xk would be the solution. So it is enough to stop here in this way and accept xk as an approximate solution. So what can be proved here is that any accumulation point of xk is a solution of the SMPEG. An interesting feature of this convergence proof is that it finally depends on a sequential optimality condition. I don't write down the sequential optimality condition here because it looks very messy, but it depends on the optimality condition. So the study of optimality condition, but sequential optimality conditions are where you don't need any conditions on the data. You just have the problem. It doesn't matter whether it's later, so it will not satisfy. It doesn't matter what it satisfies. You can always have some optimality condition. But interesting feature is that optimality condition allows us to use that optimality condition for SBP can be used to actually give a convergence to this algorithm. So that is why GD becomes a very important explanatory tool, because to start with, it shows that a nice algorithm for a nice and a simple algorithm based on optimality conditions, because otherwise, if the optimality conditions are not linked with any algorithm, this whole study becomes very strange, because sometimes like an independent thing. Usually that doesn't happen. For example, KKT conditions are very much related to convergence analysis in algorithms. They are very much related to algorithms. As a result of which that link has to be established. So it now appears to me that this sequential optimality conditions are important because they allow us to have a schematic algorithm and also get a convergence proof. So this appeared in a paper with myself, Dempe, Dean, and a PhD student of mine, which appeared in Mac Programming in maybe this year, May, I guess, May. So let us come to the last part of the story, which is that the Solodov's algorithm. This is the first, I think, algorithm for SBP. I'm sorry if I'm unaware of anything, please let me know. I would also have to have information on this. So what he does, he actually does penalization. He constructs functions like this, and where this is the lower level function and this is the upper level function. And he does a very strange thing. He is essentially telling that, okay, as epsilon k goes down to 0, I am gradually putting weight on the lower level, not on the upper level. While in the other case, I had, because of GD, when I had used GD, we had put weight on the less, as we go up, we put less on the weight on GD and more weight on the function. So he basically does the penalization, and then he minimizes, then he wants to minimize this class of functions on the set C. And then he does a projected gradient method combined with an Armizo criteria. But I think his result can also be improved. We were recently discussing with my former PhD student that because projection, once you have a projection criteria and you have something like Lipschitz gradient assumptions, you possibly do not need Armizo criteria, because you'll automatically get a descent when it decrease. So I do not know, but let us just go on with the algorithm. So what we can do, if you look at the RSBP, that is minimize fx subject to hx less than alpha and x in C, then I can penalize it in this form where epsilon k is going to 0 and all these things. Where this is the penalized form, but for every k, this is a fixed quantity. So I don't need to bother about this fixed quantity, and I can just bother about this part, which is same as the Solodov scheme. So this can be a possible motivation as to why that scheme was chosen. So here is the Solodov's algorithm. So what you do is you basically, this beta is chosen, this step length that you use in this projection, that is chosen through the application of Armizo criteria. I do not know whether it's really required or not, but the convergence proof, it seems that, okay, this might be required. So this is the idea. Projection step, choose the step length with Armizo criteria, and then keep on decreasing the value of epsilon at every step and setting k equal to k plus 1, repeat. And now how will you stop the algorithm is a question. So when we did actual computation with this algorithm, then the thing was stopped with that whenever I get an x and xk plus 1, and we put a threshold mu, and whenever xk plus 1 minus xk, the norm is strictly less than the threshold mu, you stop the thing. So there are certain conditions under which this gives me the convergence. So you are assuming SBP to be bounded. Okay, you take C to be compact, it will hold. F and H are assumed to have Lipschitz gradients. and also these conditions on C. Of course, if C is compact, these are true. And then the distance of the sequence that you generate by this iteration scheme, Solodov scheme, will go to 0. Now, the paper which we are going to submit very soon, in that paper, what we have done is that we have considered a system, a simple bilevel problem, where the upper level objective has no restriction. It can be differentiable, non-differentiable, anything, convex, of course. The lower level problem is differentiable, but it need not satisfy any Lipschitz gradient criteria. See, we were very keen to remove Lipschitz gradient criteria because then we did another work on assuming that I take an SBP and assume that both my upper and lower level has non-smooth objectives. Then I cannot really think about Lipschitz gradient criteria. And if I want to put Lipschitz-like conditions and all those things, that on subdifferentials will not satisfy those things, subdifferentials or convex functions. So the only way is to find some way out of that paradigm, that how would you, then I tried to get 2 different algorithms from 2 different papers, which are very different in nature, but has some link with SBP. And we jumbled them up into one algorithm, and it seemed to work, the convergence. So we understood that if we have structurally, if we have non-smooth and we follow what we have done here, we would possibly get rid of the Lipschitz gradient criteria, because, okay, if you have linear functions, Lipschitz gradient. If you have quadratic function, Lipschitz gradient. But given an arbitrary convex function, how do I know whether I have Lipschitz gradient? You look at the book of Amir Beck, first order optimality condition, there are few functions, and those functions may never appear in real actual applications. So getting rid of Lipschitz gradient criteria is important. So how do I get rid of that Lipschitz gradient criteria? Surprisingly, we came across a paper of USEM, and we figured out that there was a kind of Armizo decrease criteria there. If we modify it to our system and take care of what is there for the simple bilevel programming, we can modify that system and generate a descent direction and keep on using the descent method without use of Lipschitz gradient criteria. We actually successfully, we have not submitted the paper, we'll submit it very soon. We could actually do numerical experiments, and we actually show this kind of result. So that has been a interesting fact, which in fact we have tried to apply it on this kind of finding sparse solution, because the top level objective need not be convex, need not be smooth. It can be non-smooth. And we have taken a problem where everything is smooth and has Lipschitz gradient criteria, applied Solodov's algorithm and applied our algorithm. Our algorithm is much, much faster than Solodov's algorithm. So that is the work but simple bilevel programming is a very interesting thing, because many places, many applications, economics, many applications in communications. Actually, if I spoke a bit with Francisco Facchini on this, and then there are applications of this form. Actually, there was a paper by Fang and Facchini, Facchini and somebody else, in which they were looking at a very strange problem. They were telling that finding the solution of a variational inequality over the solution set of finding the solution set of a hemi-variation inequality over the solution set of a variation inequality. So they wrote some algorithms for that. From that, and then there's a paper on hierarchical optimization, where the lower level problems don't have constraints, but we have constraints. So there was this paper by Cabot, Alexander Cabot from France. So we took ideas from these 2 papers, and we made a kind of mixture of the algorithm. And that algorithm worked for us for the non-smooth case, where every level we have non-smoothness, and also for the SMPEG case. But because you have non-smoothness, you're using subdifferentials or epsilon subdifferentials. Computing them, actual computation is hard unless you have very specific structures. So that has remained a more or less a theoretical paper we submitted to optimization. And but with my PhD student and one collaborator from IIT in Bombay, we figured out, we were very lucky to get the paper of USM, that we can actually get rid of Lipschitz gradient condition and yet have upper level non-smooth, lower level smooth, yet get good results. Thank you. Uh, for example, this is a tutorial example. This is a problem where you have Lipschitz gradient. You see, this is a linear programming problem. So linear programming problem can also be put into as a bilevel programming, simple bilevel programming problem. And here the set C is Rn plus. So Rn plus you can do easy projection. I do not know whether how it would compare with simplex methods and all, but it can be done. So if you even have a quadratic programming problem with linear constraints or affine constraints, then also you can write it as a problem. And for this problem, maybe Solorov's approach or maybe our approach can actually work, which will work actually. So that's the interesting thing, that we have a new approach now to solve convex quadratic problems also, with once we have linear constraints. So there are some references. So this was a paper where this simple bilevel programming term was coined. And this is a recent book which celebrates some 80 years of bilevel programming of Stackelberg games. So in where I have a paper with my former PhD student. There's a detailed survey on algorithms for simple bilevel. I think this paper should be much well known. Solodov, very beautiful paper. And so I was lucky. I would have never known it if I had not got it from Math Reviews. And this is my last paper on this topic, which appeared. So anything. So we have few minutes to chat actually.
Okay, so thank you so much, Joydeep. So I'm just waiting if there are some questions. So meanwhile, maybe just to warm up, maybe I ask a couple of questions. So first of all, really very, very nice talk. And this approach with gap function is really interesting. Okay. So I just was wondering if you can recommend a textbook. So I know that there is by Stephen Demper from 2002, which is, I believe, quite old. And I think you were talking about, anyway, early 2000. But is there something more recent, or is it just, say, some papers published on some particular topics, or there is a...
By bilevel programming?
Yes.
There is this book, Bilevel Optimization, which appeared from Springer in 2020. The collection of papers is extensive, including they show the heuristic methods for solving bilevel programming. This collection, and this also has a work on this first is on pessimistic optimization. See, I can this book has a the first chapter of this book is on pessimistic optimization. So this is a very good book. I think bilevel programming, Stephen Dempe had another book. I'm forgetting the name. It is something to do with some applications to some chemical engineering problems or for mathematicians. So this is the latest book. I think after Stephen Dempe's book, there was no textbook at all on bilevel programming to study, to go. See, the bilevel programming, I would say that, okay, I am now really interested in this algorithmic aspect of simple bilevel programming problem. And there is this paper I just want to mention, which I find it pretty exciting. This is called Approximation Methods for Bilevel Programming by Said Ghadimi and Mengdi Wang. Both are at Department of OR and Financial Engineering, ORFE at Princeton. So what they do in this case, their lower level objective, given an X, it is always strictly convex or strongly convex in Y. So for every X, if this is the situation, then you are getting a unique solution for every X. In that situation, can we design an algorithm? The computer scientists are bringing in a very different kind of insight in our subject, because they have used more, has a more computational aspect. So they have defined a very interesting way to have an approximate solution of the bilevel problem, this bilevel problem. So what they did was, how do you minimize, right? So you take a particular K. So your xk, say you have an xk now, right? Now for xk, you try various y's, and with those y's fixed up, start with, so fix up xk, and you're trying to solve the lower level, and you know that lower level has a unique solution. So what you do, you start with some y0 there and apply a descent search. Lower level has no constraints. This is the very important thing. Once you have constraint, things will go bad. So it's a good thing to extend it to constraints. So lower level has no constraints. So they use kind of course, if you have constraint, you can put projections. So they use a descent method. So what they did, they don't take the whole descent method. They take a few steps, means they take, say tk minus 1 steps, say, so that they just bring down the function values of g. Once they have brought it down, so the last value they have got, that y bar k, that they take it to the upper level. And on the upper level, they use a proximal gradient type algorithm to solve it. So this is the way they are generating an approximate solution. And for this algorithm, they have found out complexity measures, iteration complexities. It's a very, very interesting paper, actually. Very interesting paper. So it's called Approximation Methods for Bilevel Programming, Said Gadimi and Mengdi Wang. It's a very nice paper, actually.
Yeah. Okay, thank you, Joydeep. So any more questions from the audience? I think Alex.
Hello, Alex. How are you?
Good, good. Thank you. Thank you, Joydeep. Very nice to see you finally.
Yeah, I'm also happy
quite
to see
a while.
You.
I think after 2004, you haven't been to Ballarat.
I haven't. No, I have been to Ballarat once. I think in 2000.
It was in 2004 when we had this ICOTA conference.
Yeah, at that time I came. That is why I still remember the hospitality of Nadia and Julian.
So, Joydeep, thank you very much for your presentation. Indeed, it helped me a lot to fill the gaps in my knowledge of bilevel programming, and also very well structured. Here, it of course helps memorizing and learning these things, plus the tutorial, of course. My question.
University nowadays.
My question, Joydeep, is about the way you are presenting these things. You actually started your lecture today with explaining this, and I want to bring this issue back again. So you decided to make this handwritten notes, which is definitely not usual nowadays. I can't remember when I last saw handwritten notes. So can you tell all of us why did you decided to do it this way?
I was in a conference, and I gave both I just did a handwritten part, and I just also did a slide. I showed the slide, I showed the handwritten part. The people said that they found the handwritten part, the slides at this point, that point, difficult to read, but handwritten part, because you write big and you have spaces, so people can possibly have can follow a bit. So they said, because we are looking in a computer, we can see your handwritten things clearly. So it's okay with us. I said, okay, let me just go against the tradition for once.
Yeah, I see. So it is your style, and it is your way of attracting the audience, and actually you did it very well, and very good handwriting, of course. Thank you for. I'm already thinking about actually doing it like this, but
I was very interested when I always saw Juan Enrique write on the board. On one side of the board, he will start writing with very basic things, and then one end he'll write in his beautiful handwriting. End we have come to the frontier of research, and been a postdoc with Juan Enrique and been his friend for such a long time, and so I really had been influenced by him greatly. So then I thought, let me do this experiment now because everybody can see it. So I actually, because when we discuss with students, some students want to share something in the classroom. So they will write something by hand and they'll put it, they'll scan it or something and put it there. So then you realize that possibly this is not a very bad idea. Let me try once. Yeah, first I thought, okay, you have invited me for plenary talk and all. So if I do this, people might not like it, but I think maybe try it out as an experiment. If it has worked, then it's okay.
So now I see that the roots of this method are in Barcelona.
Yeah, it's in Barcelona.
Great. I also want to mention that, of course, I was greatly impressed by this way of presenting, and you impressed me again when answering to Vera's question and then to Nadia's question. You just took a book or a paper from your shelf, and okay, this is a paper written this year, this volume, this page number. Normally, when answering this type of questions, people are looking for something on their computer. Sometimes they find, sometimes they don't. So you impressed me all the time today during your lecture. So
gold is sometimes gold.
so thank you again for your presentation, and I hope that the circumstances will allow us to meet soon at some stage. Of course, it's great to know that you successfully went out of this problem with COVID. So stay safe, please.
Now I'm feeling pretty okay. Till mid-November and October, I was feeling, if I sat for 2 hours, I felt like just going and lying down. I used to feel very tired.
So it didn't affect your handwriting. This is great. Okay, thank you very much, Joydeep, and stay safe.
Oh, thank you. Thank you. Yeah, Rainer.
Yeah, one more question, but we need to be careful with the time. So, Rainier, please.
Yeah, it's a very quick question. Thank you very much, Jody, for your very good presentation. There is some, my question is, there is some relationship between bilevel programming and integration of two convex sets. What I mean is, the solution of the first problem in the first level is a convex set, and the solution of the second level is another convex set. There is some relationship between the intersection of these two convex sets. Of course, if there is an intersection, it will be the solution in there. But what happens when it's not there are not intersection? There are some related in the solution set of these two.
You're talking about this last SBP problem, the one which this particular thing, the simple bilevel problem?
No, two bilevel problem. For example, minimize F subject to the solution of the variation inequality.
Okay. So variation inequality, the solution is a convex set, and the whole solution set is a convex set.
Yeah.
The solution, but that would be that would be inside the solution set of the variation inequality.
They will coincide.
They will be inside, not coincide. The solution. So here is the solution set of the variation inequality. Now it is the feasible set of another function. Yeah. So the final solution set would lie inside the solution set of the variation inequality. So among the many solutions of the variation inequality, I am choosing some of them through this function by minimizing some other function over it. Like, for example, I have this solution set, and then from here I choose only this part, and this part is chosen by minimizing some some function over this as the feasible set.
Yeah, but you are consider the problem with restriction. Suppose that you want to minimize f subject to that x belongs to some solution of another problem. Then you try to solve the problem independently without restriction. There are some relationship between these two sets.
Do you know any paper on this one? If you have any idea?
No.
I'm very sorry, Rene. I think I
Oh,
have
sorry,
to.
yeah.
I'm very sorry.
I will try to compose an email and send you to you.
Yeah, sure. I'll be very happy to know this.
Okay, thank you.